You're all in the right room. I'm not Evelina. Evelina is in room 1. We swapped. I'm Hannes. I'm going to talk to you today about building IoT backends in Akka.net. What I'd like to cover today, so you know what's coming, I'm going to give you a brief introduction with all you need to know about Akka.net. Then I'm going to explain to you what the problem domain was that we were working in when we did this, and what role Akka.net played in implementing the solution. And then I'll dive into some technical implementation details so you know how to do this yourself if you want to get on board. And then I'm going to put you on your way with some resources that you can use should you want to play with Akka.net yourself. And for those interested, I have stickers, so come see me after the talk if you want an Akka.net sticker to put on your laptop. So what is Akka.net? In the 70s, when people were not distracted by smartphones, a lot of research got done, and a lot of the stuff that we are using today was invented back then in theory, and it has become possible today to implement it because we have the processing power. And actor models are no different. In the early 70s, Carl Lowette and Peter Bishop, they wrote the first research paper that actually talked about implementing software with a likeness to nature. Like things in nature interact with each other, and that's what actors do. And those papers got refined during the rest of the 70s and the early 80s. A lot of people worked on that. And the first practical implementation was in the 80s. And Ericsson, we're talking about the period where telcos were making money by doing landline connections. And if you could not make connections, you wouldn't be making money. So reliability was a very, very important factor for them. But of course, nobody had made an implementation. So they invented their own programming language, which is Erlang. And they invented that to build the AXD 301 telco system. And their focus was on being very performant, very fault tolerant, distributed concurrent, all these things that we value now. And they managed to get 9 nines uptime with a code base that had about 2 million lines of code, which is impressive. It's even more impressive if you put that like in real time, because that means that you will get 31 milliseconds of downtime per year. I don't know about your code, but I don't achieve that. So yeah, if this has been around since the 70s and the 80s, why did we only get it in higher programming languages later on? Because if we look at where Akka.net comes from, in 2010, there was a implementation of the actor model on the Java virtual machine, which is Scala. And they actually implemented Akka. And only in 2013, 2 people individually from each other started porting Akka to the .NET CLR. Aaron Stannard and Roger Johansson, they started working on that separately from each other. And then they found out about each other's efforts. So they decided like, okay, let's take the good things from your code base and like, take the good things from mine and combine it and make it into one effort. And they actually got permission to call it Akka.net from the original Akka people on the JVM. And in 2015, we got the first production release. By now, the team is a lot bigger than the 2 of them. It has become very stable. We're very close to getting the 1.4 release, which will improve networking performance. So yeah, it became a very, very stable effort. Now, what happened in 2015 is that on the .NET ecosystem, we got 3 actor model implementations over the course of a few months. Microsoft open sourced Project Orleans, which they used to build the backend for Halo 4. And the thing with games is, you get most of your revenue the first couple of weeks after release. If your backend cannot keep up, people cannot play. If people cannot play, you get bad reviews. If you get bad reviews, you don't get sales. So they needed something that they could very, very easily scale. And they had all the processing power because they had Azure and the backend for Office 365. They had the servers, but they needed like the programming model, so they built Orleans. But in the meanwhile, the Azure team was working on Azure's Service Fabric. And on Service Fabric, you also have the Service Fabric reliable actors. And then the guys that I just talked to you about, they also released Akka.NET. So why, if all of this has been around since the 70s and the 80s, that we only get it in 2015? That's a question you should ask yourself. Now the thing is, classic scaling around that time went through a bit of a crisis because the web was booming because of smartphones and IoT devices and all that sort of stuff. And the fact that you could deploy an app into the App Store, you couldn't predict how many users you would get. So if you do like a classic web application, you would start building a cluster of web servers, and if they couldn't keep up anymore, then you would like increase the scale of your database cluster and add a caching cluster and so on, and it became really complex. And it's really hard to do. If you've tried doing this, you know that there's no free lunch. And then the second problem is the evolution in processors. Because if you look at this thread, this is basically what happened in terms of transistors and clock speed and single thread performance to the processor landscape. And there is 3 lines that are really important to notice. Is that clock speeds, they have stabilized for over a decade. Like we've had 3 gigahertz processors for a very, very, very long time. And I don't think anybody sells anything over 5 gigahertz commercially anyway. So that has stabilized. Single thread performance is actually stabilizing as we speak. But there's one line that is increasing a lot, and that is the number of cores. You probably have more cores in your phone right now than you used to have in your laptop 10 years ago. So that is the number that we want to exploit if we want to build something scalable, right? Now, the thing is, if you've tried parallelizing code, that is no easy thing to do. Who here has tried to manage a thread pool manually in .NET or another higher programming language? Yeah, was that fun? No. The problem is always shared state. Because as soon, and you're always going to have to share state between threads. I mean, otherwise your threads are not doing anything. If you have shared state, that means that you will have race conditions, you will need to implement blocking, there could be deadlocks, all these parts that you're going to have to do that are going to hurt your scalability. And if you look at Amdahl's law, he thought about this. This is a graph that shows you the theoretical speed up that you can get by adding more processors in relation to the amount of code that can be parallelized. So if you have only 5% of your code that needs to run in series and all of the rest of the code can be parallelized as much as you want, you will never get more than a 20 times increase in speed. So even if you throw 65,000 processors at it, you will only be able to handle 20 times the workload. So if you want to build something that is really, really, really big, 90% or 95% is not going to be good enough. So that's where the actor models try to help. We're going to try to achieve a very, 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 very high degree of parallelization with stateful systems. Because if you have to implement something that's completely stateless, that's really easy to do. If there's no state, you can just parallelize everything. But if you have state, it becomes harder. And they do this by doing reactive patterns and to have also fault tolerance built in so that if something crashes, not the whole cluster goes down, it's just this one error that occurs, and you keep running. Any of you know Randall Munroe? Great book. Recommend to read. So I'm going to explain how that works. And the basic building block of the actor model is, of course, the actor. And an actor is a very, very simple object. I'm going to show you in code in a second how that looks. But the actor has an inbox. And it's a first in, first out messaging inbox. And that's the only way you can talk to an actor. You send it messages. And then the messages will get scheduled on the actor to be processed. And your actor will have all its state and all its behavior and all its code internal to the object. There is no other way to communicate with it. And when you process all these messages in order, you know that you're on a single thread. So you don't have to write any code to make sure that it's thread safe, because every actor will only run on a single thread. There will never be two messages processing at the same time. And that makes a lot of things a lot easier. So if you look at the most simple actor you can write, this is an untyped actor. It's a class you inherit, you implement from the Akka.NET package, and you will have an onReceive method. And the onReceive is the method where all your messages come in. You can figure out what type of message you're getting and process it. This is like the simplest form of an actor that you can have, right? Now, what is very important about these messages? The messages are simple classes as well. You don't even have to inherit anything or implement any interfaces. It's just like a basic class. Now, the thing that you have to pay attention for is that they have to be immutable. Because the Akka.NET runtime does not enforce them to be immutable, but it expects them to be. So in theory, as soon as your message crosses a machine boundary, you no longer have that problem, because it gets serialized and deserialized and serialized. So then you break the reference that you have to your object. But in theory, you could send a message to another actor and then keep a reference to that object. And as long as you're on the same machine, that is still like a CLR object that you can change. Don't do that. You're going to have a bad time. So it's very easy to manipulate that, but just don't do it. It'll cause all sorts of problems. Now, in throughput, they claim that they can process about 50 million messages a second on a single machine. I have no reason to doubt that. I can easily get over 1 million messages a second on my laptop. So if you have like a serious server, you can probably achieve those numbers. So how do you do that with immutable messages? You just make sure that everything only has getter properties. The only tricky part is every type of collection. Now you have the system.collections.immutable namespace, where you basically get collections where you cannot add or remove items anymore. So use those in your messages and you're going to be fine. And then the most important thing is the actor system itself. Because you have all these actors, but something will need to manage the life cycle of your actors. It needs to spin them up, it needs to dispatch messages to them, it needs to manage all these inboxes, because it could be that an actor has a full inbox of messages waiting, and it needs to do all the thread scheduling for you. And that's the thing that we're really happy about, because we don't want to do that ourselves, right? There's also a system event bus for if you want to do publish subscribe between actors. I'm not going to dive into that today, but know that it's there. It's basically your big puppet master, right? This is still by far the best Metallica album ever, and if you disagree, you're wrong. No, an actor system. If you have to create that in code, it's actually really easy. You go actor system.create, you give your actor system a name, and that's it. Now, what is important is if you want to deploy actors to your actor system, you will always do so through something called props. What are props? Props is basically, you could see it as a pointer to the constructor of your actor. You can tell the actor system how it needs to instantiate your actor, and then the actor system will do that for you. This makes sure that you will never have a reference to your actor from the outside. You will have something called an iActorRef. Like this myActor variable here will be an iActor reference. And you can use that to talk to your actor. You can send it messages. So you just instantiate an object as a message class and you do your actor_ref.tell is exactly how you dispatch a message to your actor, right? And then the actor system will take care of that for you. Now, actors live in a hierarchy. There's 3 actors that's always present. It's the root actor, the user, and the system actor. These are the top level actors. These are the system actors. And then below the user one, that's where you create your actors. The top level actors are the ones that are directly under the user actor. And then below that, everything, every actor can spawn children, as many as they want. Now, the thing is, the only thing that's really important in this to remember is that your address is your place in this tree. So this B3 fellow at the bottom, his address is /user/a2/b3. And that becomes very important later on, that you can address these actors by their address. Now, to make sure that if an exception occurs in this whole actor hierarchy, which are all processing their messages, and to make sure that that exception stays contained, we have a concept called supervision. How many of you have children? Yeah, right. So, take your children to a supermarket. Who is responsible? You are, right? If they fuck up, you have to clean up the mess, right? That's exactly how that works in an actor system. If you spawn children, you are then responsible for supervising all the errors that they cause. Which is actually a very, very flexible concept. If an exception occurs in an actor, the parent will actually have a strategy on what needs to happen. You can choose to resume, which is basically, okay, that's not bad, just continue. Or you can restart the actor. It's like, okay, we're gonna start over, see what happens. And then the message, the inbox of the actor gets preserved. So that's a good thing, but the state is discarded. And then you have the fact like, okay, yeah, that messes everything up. Just stop what you're doing. We're gonna figure out something else. And you can do this for only the failing child or for all the children. This is the most important concept in fault tolerance in actor models, right? You make sure that if an exception occurs, it occurs somewhere in the bottom where it doesn't really affect anything else. So if you're gonna do something risky, you just push it onto an actor and then see what happens. Now in general, if you start programming in this, you're gonna need to think about your code a little bit differently. You're used to doing object-oriented. A lot of that will transfer to this. But the main ideas, and everything comes down to this again, is like you're gonna split your workloads into very, very small tasks. And you're gonna make separate actors to process all these tasks. And then you're gonna send that work to them. And you push all the risk to the bottom. Because if it fails there, it's very contained. And one thing you need to watch out for is that you don't create any bottleneck actors. There is something like overflowing mailboxes because an actor runs on a single thread. So if you give it more messages than it can process on a single thread, then you're gonna have an ever-growing inbox. But you can avoid that by making sure that your message flows or models do not have those. There's a whole bunch of design patterns that go with this. Basically, the one that I just explained to you is like you split all the work and you divide it over your children, which is the fan-out pattern. But there's also some proxy patterns that you would need to use to avoid faults when you go over network boundaries, which could happen. And then there's a whole course, I think it's a 4-hour web course that Petabridge does. Petabridge is the company that was erected by Aaron Stannard and Roger Johansson. They actually give production support on Akka.net. You can follow that course and you will get into all these things. There's just one of them that I didn't want to withhold, which is the character actor pattern. Anybody watches Star Trek here? Okay, what happens in Star Trek if you have like a guest actor, somebody famous who comes in for like an episode or two? They arrive at a new planet and they send that guy down first, and he dies, right? Well, why do they do this? They want to keep their main cast alive, because the main cast is important to the series. You want them to be alive by the end, right? But sometimes for the storyline, somebody has to die. So you get a character actor in, they play this one role, they die, that's okay because the series moves on. And that's what you do with actors as well. If you know that you're going to do something risky, gonna go over the network, gonna go to the database, I don't know, you're gonna do something that might fail, you push it onto a separate actor. And you just monitor that for failure. And you deal with the failure or success of that actor. But if that one fails, your state is preserved because your actor did not die. That's what you call the character actor, right? If you do a risky operation, you spawn a child, you delegate your risky operation to them, and you handle it. I think that's enough information about actors. Is that a little bit clear for you how that pieces together? Okay, let's get into our problem domain then. Do these look familiar to you? That's what my meters look like in Belgium. It's like electricity, gas, water. Now, this was basically what we were working on. We were building a metering backend for these and their more modern varieties that did have digital connections. But we could actually implement some optical readers on these and still get like these meters to connect to the backend as well. So how did that look in our connected situation is you would have a meter in your house, we would connect an IoT device to that would get the meter readings from them. It would send it over the internet to our backend, and our backend was then used to present information on your smartphone. It would have a web portal where you could configure alerts, all that sort of stuff. That was what we were building. The red part is what we're going to be talking about. One important concept to grasp before we dive into this is the reading versus consumption problem. These devices, I'm going to go back for a second, these devices, they have numbers on them. Well, the number by itself doesn't really mean anything because you could have bought the house and there would already be a reading on there. What is important to you is like, okay, how much did that reading change regarding to the last time that I checked? That is your consumption. That is the thing that you're going to get billed for. That is the thing that you're probably going to care about, not about the number per se. So the blue line would be our meter readings, but then the difference between that and the previous 5-minute mark is basically what we consumed. And that's the thing that is interesting to work with. So what did we want to do with these readings? We want to store all of them for all eternity so that we would have historic usage data for analysis. So we wanted to store all the normalized values. We wanted to be able to plot graphs on top of that. We wanted to compare time periods, and then we wanted to have alerting on them. We did have some machine learning that would detect unusual situations, not what we're going to talk about today, but we wanted to present some alerts to the user on their phones, like, hey, something is happening in your house that is not correct, please go check. Usually it's when consumption exceeded certain thresholds. This is really clear. If I want my consumption to never exceed the red line, then at 10:30 I would get an alert on my phone, right? What becomes a lot harder is if you look at a periodic threshold. It's like, yeah, I don't want to go over a certain line for the next 20 minutes. And then it becomes a business discussion that you're going to need to have. Because that red line, it's very clear. You've been over that red line for 20 minutes. That's very clear. You should trigger an alert. Now the green line is a different story. You exceeded it a few times. You didn't exceed it every time block, but still you exceeded it on average. There is no correct answer, but that's the kind of discussions that you're going to have with your business when you get into this, right? So that it behaves as expected. So basically that's what the part of the problem that we're going to look at today. Now, how does Akka.net fit into this? If you're going to build an IoT stack on the .NET ecosystem, chances are that you're going to look at Azure. And your typical IoT stack will have to have a few things. And the first thing is the communication to your devices. Somebody has already solved that problem for you, But what you're basically going to want to do is your devices will authenticate against your backend. They will send you events, so you will need to be able to accept messages from your devices. You would have to detect if they are online, like presence detection, very important thing. And then you would want to send control to them. Turn on the lights, set the set point of your thermostat, that sort of thing, right? You get all that out of the box in IoT Hub. Don't write it yourself. We did, because we started before IoT Hub existed. I would not do it again. Now, next to that, that is how you connect to your devices, but then you're going to need to start processing data and store it. So you're going to have to look at all these compute components, probably going to look at Azure Functions or Service Fabric. You're probably going to use some queues somewhere, use service bus, stream analytics, and then you're going to store it in various ways. If you want to store lots of bulk data, like time-stamped bulk data, you could basically dump that into a blob per device. That works really well because blobs have indexed search. So if you know when the blob started, you can point to a certain location in the blob and just read some data there. That's the data you're going to need. If you need to store lots of sensor data really cheaply, that's a way to do it. But you can use like Cosmos DB or Azure SQL, whatever you need. And then you still haven't created any business value yet. Then you're going to need to present that data in portals and apps and run analytics on that and machine learning and all of that. So you're going to use things like app services, Service Fabric. You're going to use Notification Hub to push your notifications to your devices. You could use Power BI to build some dashboards. Now, not all of this can be done by Akka.net. I mean, basically the compute and analytics part is where it would be useful to use an actor model. Because that's what it's really good at. I wouldn't build a website using Akka.net per se. It could talk to it in the backend, but there's no added value. So what our setup looked like is we had an Akka.net cluster. The Akka.net cluster talked to all of the storage components that we had. And on top of that, we had the web portal that basically talked to the cluster to present the data to the user. And then on the device side, we had IoT Hub talk to the devices. And then you had an event stream. You familiar with IoT Hub or Event Hub on Azure? It's basically a string of messages and you have a pointer and you can move your own pointer, right? So you start reading at a certain point and then you get all the messages. So we had an app service that had a pointer and that would relay the messages to the Akka.net cluster. So this is a pet peeve of mine. Don't be a magpie, okay? You all know about the magpie, black and white bird, like shiny things. Don't be that developer. Don't use a framework because you want to use it. Use it because it's appropriate for your use case. So Akka.net is useful if you need to build something that has lots of state and needs lots of throughput, and you want to have a high degree of parallelization. Trading systems, gaming backends, IoT applications, I mean everything that you want to highly parallelize, that is what it's good for. But it's always going to be part of the solution. So I'm going to show you a few of the important parts of our actual implementation of this so that you can understand how it all pieces together. These are the 4 things that I'm going to explain, and then I'm going to let you have your lunch. The first tricky thing is, if you look back at this graph, you see that the Akka.net cluster runs by itself. And if you remember from a few slides ago, sending a message to it was done in process, right? You had the actor system, and then you could get an actor reference by creating it with props. But we're not going to do that over the network. So we have to run our actor system as a cluster. And the way that we do that is to use remoting. And the funny thing about this is, if you want to talk to an actor system remotely, you create your own actor system locally, because actor systems can talk to each other. And that's what Akka.remote does. The cool thing is, this is like 100% transparent. So you have an address, and you know that you're going to talk to an actor system that lives somewhere else. You're going to have your protocol. This is like a URL that you could see in any protocol, right? You have a protocol, the name of your actor system, the address where it is on the network, and then the location of your actor, right? That is your actor path. Now the thing is, you can even create that actor remotely. So you can basically tell it to create that actor at that location, and then the other actor system will create it for you. Now what the funny thing is, I talked to you about these iActor refs, right? The one that you got back when you created your actors with your props. Those objects are completely location transparent and you can pass them around. So if you have an actor ref to a certain actor, you can just pass it over the network as a message, and that one will get the iActor ref and it can talk to the actor that it points to even if it lives somewhere else. That's what we call location transparency, and that's really important in this whole scenario. There are more transports than just TCP. One of the big upgrades in Akka.NET 1.4 that's coming out in a few weeks, they released beta 4 yesterday, I think, is that there's going to be some performance improvements on the TCP protocol. Not that it's slow now, it's just going to be lots faster when we're done. So, what did it look like for us? This is the getting your messages to your actor system. On the right, you will see the Akka.NET cluster. That's where all the actors for our devices live. On the left, you will see the app service that reads from the IoT hub event stream, and that wants to dispatch all the messages to the remote actor system. And how that works is you create an actor system in your client. That's your client actor system. And you're going to have a bunch of actors there. So what I will do is I will create a proxy actor for every device, identified by its UUID. And I will create that proxy actor, and that proxy actor on startup will talk to the remote actor system, and it will ask the top level actor there. It will send a connect message. It's like, hey, I'm device with UUID, blah, blah, blah. And that actor will actually figure out if the device already exists. If it doesn't, it creates it. And then it will pass the iActor ref back to the device proxy. The reason that we do this is if this one has an iActor ref in memory, everything is a lot faster. You can talk to it by address, but then you use an actor selection, and actor selections are way slower than iActor references. And from then on, basically any message that comes in from the event stream can get relayed to that one, and that one can talk to the device actor directly. This is basically how you run that whole proxy remoting thing. And the fun thing is you can extend your proxies to detect if the other side is still present, because that will actually get messages in that you can subscribe to if the messages that it tries to send to the other side, if they fail. So then you can retry and that sort of stuff. What does that look like in code? And this is a very busy slide, I'm really sorry. But the important things are your actors can have a pre-start method. And that is code that gets executed before it accepts its first message. And that is very beneficial because this code here in the pre-start, it will make that connection to the other side. So what it does is we have that top level actor and we define that as an address, and the remote actor system is basically the protocol and the network address of our remote actor system. And we talk to it, and we use an actor selection. And that doesn't really matter. I told you that actor selections are slower than actor references, but this only happens once per device after startup. Doesn't matter if this is a little bit slower. You get an actor selection. You can talk to an actor selection as well by just using tell, and you send the connect device message to the other side. And then the other actor will basically reply to its sender, which is very useful. And that will come here, and you will have the handle device connected message will come in. And you will basically now have your reference to the other side that you can talk to. Now you notice that we are not using an untyped actor anymore, but we have a receive actor. And a receive actor is a more strongly typed version of the actor. And basically what you can do in the constructor, you can have these receive methods for various message types. It looks a lot cleaner. For me as an OO developer, this is like, it feels like I'm doing the right thing and all my functions are single responsibility. So every time this proxy gets a message, it can now just forward it to the device actor which lives on the other side. And this is a tip that I'm going to give you. What I always do is, you remember those props to create actors. What I always do on every actor is I make a static method that I call create props that maps all the parameters. Because you have this props create and you give it all the constructor parameters. And you see this constructor parameter maps to that one. Now, that is in no way strongly typed. So you can do create props and then you have a params array. And if you refactor your constructor and you add or you remove a parameter, your compiler is not going to break. But it does if you do it like this. I make sure that I only consume the create props, and I make sure that that maps with the constructor at the top. And then if I want to refactor my constructor, I know exactly where in my code that was used, because that will actually break upon compilation. Did that make sense? If I told you that? Okay, good. Now, the top-level actor on the other side, the devices actor, the one that receives that connect message and has to reply, that basically checks if its dictionary of actor references already contains this UUID. If it doesn't, it creates it, and then it will just reply with a response, and you can do sender.tell. Because you know your actor is single-threaded, which means before you start processing the message, a lot of stuff is set on the execution context of your actor. And every actor class has a sender property, which is basically a reference to the one who sent you this message. And there's a bunch more. You have like a context. There's a whole bunch of things that you have available to you on that thread that is set before the message is dispatched. And because you're the only one processing, it will always work out. One thing is important though. An address needs to be unique in the hierarchy. So if you have our setup like it was, you will need to include your device ID in the address somehow, because otherwise your addresses are not unique in the hierarchy. So that's one thing that you need to look out for. That is how we got our messages to our Akka cluster. The next thing that we need to think about is how we normalize data. Because your business logic is really easy to reason about. You're talking to a business owner, it's like, yeah, think about this alerting situation. That is really easy to reason about. But in the real world, your data will not look like that. So you might want to normalize what you do. And it becomes a lot easier, from my experience, if you normalize the data stream that comes in, and then only use the normalized data downstream, it becomes a lot easier when you know that there are no gaps, that timestamps are consistent, all that sort of stuff. These meters, even the ones that do have serial ports, they sometimes send gibberish. And well, if it's like a message that is corrupt, you might detect it. Sometimes it's just like a single number that flips. But that might change your meter reading, which means you might get a huge peak in your graph, for instance. It happens. These are in no way perfect devices. So in my code base, I always want to deal with that in one place. And if you look at that in a table, if you have a very consistent consumption of 60 kilowatt hours every minute, then it would look like this. But you would maybe get measurements at 25 seconds past, or this timestamp could drift. Sometimes these are very, very, very low-powered CPUs, and you would get a reading every 25 seconds, but it would be 25 seconds since the last time it finished processing, but because the CPUs are so slow, that could take like half a second. So over time, you would drift. And that's okay if you fix that in one place. So what we did, we wanted to have like a value every 5 minutes exactly, like on the 5-minute mark, because that became really easy to reason about. And then we would normalize the reading and the consumption. And it's simple interpolation that is not really hard to do. So you take that data, put it into a bucket, summarize it, and then all the business logic will work on the data on the right. But the biggest problem is gap filling, because these devices, they live at your customer, and their internet connections are not reliable, especially if you're in Australia, as we learned yesterday evening. Now, if you miss a couple of buckets, what do you want to do with that? And that's a business decision. It's not your decision as a developer, because fixing this is really easy, but there is no right answer. I thought about it for like 5 minutes, and there's at least 6 ways to solve this. And actually the one that we used was another one than this, so there's 7. You can choose to just not fill it, and you will have a gap in your graph. Or you could like do the diff between the last blue dot and the first one and just like put it as one peak value. All the consumption in one bucket. It's usually not what you want, because you will trigger alerts that way. Yeah, and you can put that peak in the beginning of your time period, or at the end, or in the middle. You can choose to take that value and split it evenly. And in a graph like this one, that might make sense, but if your device has been offline for 3 days, splitting it evenly doesn't make sense at all, because your power consumption or your water consumption is not linear. So you might like plot it out over a trend line. It's like we take the value before it and the value after, and we just plot it on the line. Even that is wrong. So what we eventually did is we would look at the same time period last week and see how the graph evolved, and then build a similar shape which amounted to the amount of the consumption that we knew that we had in our gap. That was like the closest approximation that we could get to being correct. It's still wrong, but it's, for our purposes, it was okay. So gap filling is something that you're going to have to talk to your business, and sometimes you're going to have to decide to notify your downstream actors like, hey, this is gap filled data. Because you might want to decide to maybe not trigger alerts on gap filled data, right? Now, how does that work if you're writing the code? If you receive these meter readings on your device actor, you have a normalization actor as a child that takes in all these readings. And you just forward your incoming meter readings to your normalization actor. That one does all the math that you decided to use to normalize it. And then you send normalized meter readings back up to your parent. And parent is another one of those properties that is always filled on the thread of your actor. And all the downstream actors from there on, they will just use the normalized data. This is a very easy setup, and it makes the rest of your actors a lot simpler. Now another thing, and that we haven't discussed this yet, but you realize that until now we've always talked about state being properties on your objects, right? Data internal to your object. And what happens if you recycle the process, all of that is gone. What happens if your actor faults and it asks its parents and it gets rebooted because of your supervision strategy, the data on that actor is also gone. You can preserve the mailbox, you cannot preserve the state. So how do we deal with that? Actually, there's a library called Akka persistence. And instead of implementing the untyped actor or the typed actor, you can basically use the persistent actor, and there's like a persistent typed actor as well. Basically, you give the actor that you want to persist state from, you give it a persistence ID. That needs to be unique, because that's going to be the key in your database. And then you can call persist whenever you feel that a state needs persisting. And it's basically an event-sourced system, so you are going to persist events, and they will replay upon restart, right? You can persist commands, you can save snapshots, because you don't want to replay all events for all eternity. You want to start from like a fixed point in time and just replay the last bit. And when your actor is created and it is a persisted actor, it will actually query the database, get all the commands that were persisted out. It will restore your last snapshot. It will replay all the commands, and you will be in sync again, right? You familiar with event sourcing as a concept? Cool. So how do you do that? This is the receive persistent actor. And now you have to start thinking about the difference between actual commands and recover messages, because they are different things. I will see on the next slide what that means for your business logic. This persistent ID has to be unique, so we put the device ID in there. And then we will send, every command will go to the handle command message, and then every recovery will go to the internal handle message. There are some recovery methods for snapshot, and you can basically, because saving a snapshot is an async method, you can get a result from that operation. If it's important to you to know if your snapshot succeeded or not, it doesn't really matter if you miss a snapshot in most scenarios, because you will just recover from the previous snapshot. But if it's important to your logic to know if the snapshot succeeded, you can subscribe to these two, the save success and the save failure. Now, if you handle your command, you're going to call the persist method. And the persist method has two parameters. First is the message that you would like to persist. And the second is the internal business logic that you would like to call when the persist is successful. And it does these two things in sync, right? So if the persist fails, it will not actually move on and handle the internal message. And then your business logic you're going to write down here. Because if you're recovering from a previous state, you don't want to persist the messages again, right? You don't want to have a persist in there, because then you will have this loop of never-ending persistence. And every 100 messages, you can then maybe decide to just make a snapshot. What I usually do is I create a state object for my actor that includes all the state that I want to persist. Makes it a lot easier, because you can just go like save snapshot state, and you don't have to think about which fields you still need to fill. And your snapshot offer, when that restores, that is basically if you reboot a persistent actor, that's the first thing that's going to come in. You're going to get a snapshot offer, if you have snapshots. Then it's going to replay all the messages from the persisted queue, and only then does it start accepting new messages. Now, how does that piece into our device situation? Remember, we want to store all historic values, not just the values that we're working with right now. So what we did is we had a value storage actor, which was a persistent actor with the mechanisms that I just explained. And that one used to keep a working set of data that was big enough to handle all the runtime data, all the alerts that we needed to process, all the business logic, but not data for all eternity. So if data would fall outside of that window, it would get relayed one level down to another actor that would basically save it to permanent storage, so that we could later requery it back, but it wouldn't have to get rebuilt every time the actor system rebooted. We just want to have the working set that is enough to do our operations. We didn't want to get all data for all eternity back up to our value storage actor, right? Because that's important. We wanted to have a restart behavior, because in the real world, you're gonna like build new features and you're gonna need to redeploy, which usually means that you need to reboot your Akka cluster. So you need to get all that state back up and running after you redeploy a new version of your code, and get back up and running as quickly as you can. So recreating your actors is not really that hard. You query the database for the actors that are supposed to be there, and you just spawn children. And they will all query the persistence database for their snapshots and their events. Now that works really well, because they're all single table selects and they all query by key, so it's really snap fast. You can restore 1 million actors in no time. The problem is, if you make all your actors persistent, your database connection is going to become extremely chatty. And that will become your bottleneck. So our strategy was to have one actor that basically persisted all the data per device, and all the rest of the actors, if they needed to restore their state, they would actually query that actor. And if you remember, first we get our snapshot, then we get our events, and only then do we start accepting messages from other actors. So if other actors send a message to query the state that they need, the persistent actor will have rebuilt and will have that state in memory, and it can respond with it to the other actors. By minimizing this, you can basically improve the scaling of your restart behavior after you deploy. So we did that. We had a value storage actor, and the normalization actor needs data to work with because it needs to know what the previous message was that it got. So which will just ask the value storage actor for that upon startup. All the alerts actors will do the same thing. And that's how you basically make that work. And if you piece all this together in a good way, you can basically get up to running really quickly after a restart. That's the stuff that I wanted to talk to you about today. Now, if you want to move further from this, there's still so much stuff that I did not talk about. The first thing is, if you are going to run this in production, you're gonna need to deal with Akka configuration. You're gonna need to configure your cluster. You're gonna use HOCON for that. The human optimized configuration object notation, I think it is. You're gonna need to set up your clustering. Didn't cover that today either. You're gonna probably want to use logging and dependency injection at some point. And you're gonna want to monitor your production environment. Petabridge has a product for that. It's called Phobos. It's really good. So those are the things that we didn't cover today, but if you wanna run in a production, you're gonna need all this. If you wanna start learning about Akka.net, there is a bootcamp by Petabridge, which is free. You can just go to GitHub, you can do it by yourself. It's self-paced learning. It's really good. It gets you acquainted with all the concepts of Akka.net. And also on Plural's site, you can find some pretty good stuff. The Petabridge blog is a gold mine of information. Every new feature that they build, they blog about with code samples and everything. So most of the stuff you can find on there. And then there's the online trainings that I talked to you about earlier. They are paid. They're quite affordable. I had most value from that by first trying the above three things and like building a system until I had real questions that I couldn't solve myself. And then it's really worth doing it because they do it in a webcast with a small group and you can ask questions directly to the people who built the framework. So you're gonna get real answers as well. Also for your deployment, I covered a little bit how we rebuild our data. On the other side of the deployment, you're also gonna need to take care of a few things. You're gonna need to stop that app service and pause it so that it doesn't keep sending messages to your cluster. You're gonna need to have your cluster finish processing. Then you can stop your cluster, redeploy it, and then resume the event stream. If you do this right, you will not lose any data. You can redeploy your application without any problems. So in conclusion, first, you need to check if your problem domain is fit for actors. If it is, you're gonna have to decide which part of it you're gonna use Akka.net for. You have to design your actor hierarchies appropriately. Think about persistence, think about bottlenecks, think about fault tolerance, which risky operations you're gonna do where. Normalizing your data will help a lot if you work with IoT devices. And you're gonna have to think about the whole deployment and recycle process because that will become a deal. This was my talk for today. My name is Hannes. I work for Access in Belgium. That's my Twitter handle and my ICQ number. Make ICQ great again. You can find a complete solution with all the stuff that we talked about on GitHub. Check that out. There's a lot more in there than we covered today. So feel free to look at that, ask me some questions over Twitter, whatever. Tonight we're going to do this fun thing in a pub not too far from here. There will be 12 people doing funny talks. If you haven't bought your ticket yet, I encourage you to do so. Food and drinks are included with your ticket. It's gonna be fun. Ask me some questions.
So how do you deploy all your
That's a good question. The question is, how do you deploy your actors? Do you deploy that as a monolith? Your actor system needs to know about the assemblies that contain your actors, because otherwise it cannot instantiate them, because you will hand it constructor pointers through props. You can spread them over as many assemblies as you want, but your actor system needs to have references to all those assemblies in runtime, right? So whether you do that by just deploying a separate assembly and then when you start your actor system, you scan them through reflection, that would work just as well. But usually it's easier to have indeed one monolithic deployment for your actor system that has all the assemblies for all the actors in it.
You just deploy the same system to all the nodes that you have.
To all the nodes, exactly, yes.
You were remoting to another system. Was that just run as an executable, or was it run as a service? Or?
I put that into the question is, how do you run that remoting part? We deployed that as an app service, which also has a reference. It has to have a reference to the Akka libraries, and it has to have a reference to your message classes because it needs to send those. It doesn't need to have a reference to all the actors that live on the other side because it will only get actor references from them. We did an app service because that's easy on Azure and we didn't need to manage a server for that. But you can basically do it in any type of process that you want. So if our website would also have a remoting actor system in it, so our ASP.NET application would have a static instance for the remoting actor system to talk to the cluster to get data to present to the user. So basically, you'll start building these small remoting actor systems with the stuff that you need to talk to your big cluster, and those go inside the .NET process that needs to talk to it. But it could be anything, from a console app to full-blown web application, doesn't really matter. If it runs .NET, you can talk to it.
In your cluster, you've got actor systems running on multiple nodes in the cluster.
Yes.
How's the synchronization there working between all of them? Is there some sort of shared state?
Okay. The question is, how does the state work in an Akka.NET cluster? Basically, if you have a cluster, all the nodes talk to each other through remoting in the background as well. But you don't need to manage that yourselves because inside the cluster, addressing is transparent. You don't need to know which node the actor lives on. You will provide your actor classes with a shard key. The shard key needs to be unique, and based on the shard key, your actual actors will be put on a certain node. So you have some control over where your actors go through the shard key. But you have to remember that your shard key needs to stay the same when you recycle the actor and create a new instance. So don't use the built-in get hash code or anything to create a shard key for your actors because you're going to have a really bad time. It needs to be consistent between instantiations. But that's, yeah, I could go into that into more depth, but it will take us a long time. See me afterwards if you have more questions about that. You all ready for lunch now? Okay.